Hello everyone. Welcome to Crafting a Scalable AI for a AAA Souls-like game in Unreal Engine. I will talk to you about three systems we craft for Lords of the Fallen and how we adapt them for future releases and hopefully other IPs within the CA Games catalog. The talk will be divided in three parts. One is navigation and how we solve navigation when you have many different enemy sizes. Decision making, how we move from massive behavior trees to something more manageable through data-driven approach, and combat, couple situations that happen in combat games that are common to other genres. I'm Bruno Robaque. I'm a senior AI programmer. I work for CA Games. I'm currently working on Lords of the Fallen 2. Before I worked on Lords of the Fallen reboot, and before that, The Ascent and Sackboy: A Big Adventure. Aside my work, I also contribute with small AI articles in the Game AI Uncover series by Paul Roberts. I really recommend the books if you are into AI. Lords of the Fallen, from a developer project context, it was built on top of three principles: fast iteration, short development time, and long time support. We started in 2020 using Unreal 4. A year later, we moved to Unreal 5. And in 2023, we released using Unreal 5.3. It took about 3 years to make the game. We continue support, we still do. And in 2025, we did a major revamp of the gameplay in the 2.0 patch. We released for all the major consoles and for PC, and for performance, we kept in mind what is a mid and low hardware PC specs by 2020 standards. As a game context for an AI developer, it's a fast-paced and reactive combat, very large worlds filled with many different environments and a vast variety of enemies, both in behavior and sizes. And that variety and sizes took us to navigation. Because CPU limitations by the hardware we wanted to target, we couldn't use runtime dynamic generation. We had to use a form of static, dynamic with modifiers only. And because memory limitations, we couldn't have all the nav data loaded at all times. So word partition was not a thing when we started the game. So we used the old system word composition with sub-levels, where we place our nav bounce volumes, we generate the nav data in the sub-levels, and we stream in and out the nav data as we go. Our first issue was we had too many nav agents. In Unreal, when you want to generate nav data, you configure what is called a nav agent, a set of configurations to define how your nav data is generated. Among them, you have the nav agent radius. This is the distance you set between your nav border and your objects. This guarantees two things. One is if your enemy, your AI, has the same capsule radius as the nav agent radius, it will never collide against the objects in the environment, and you will never get nav data in places too narrow for any AI to fit in. In a simple game where you only have humans or the same size AIs, you just need one nav agent configuration. You might have a bigger vehicle or a bigger animal or something like that, and you might need another nav data set. And you will have both of them, and you will use one or the other depending on your AI size. But when you have a blank slate for your designers and artists, this happens. You get lots of AI archetypes with many different capsule sizes. And this is not manageable with AI agents because you will generate a lot of nav data everywhere in the world. If you create a new enemy, you will need to be sure you have a nav AI agent that matches that radius. If you move that enemy to other part of the world while iterating, you will need to revisit the nav volumes there, make sure you generate just enough nav data for it, not more nor less, because you will waste memory. And it all sounded like a tedious task from the beginning. So we decided to go a different way. In an ideal scenario, you will have this. You will have just one nav mesh, the green one. And if you path with a small enemy, the small enemy will automatically know, hey, these corridors are wide enough for me. I can path through them. If you path with a bigger enemy, it will know, the first two ones are too narrow, but they can use the last one. So we'll path through that. The way to do this is to have that information in the nav data itself. So when you generate nav data, you get this. First, you get your nav data split in tiles. When you use a static generation, the nav tiles you get during cooking times are the ones you will have. You don't add or remove tiles in runtime. A nav tile is the big yellow square there. If you zoom in a nav tile, you get the nav polygons. This is your nav mesh geometry. This is what is used by the path calculation to calculate a path. And there is also another piece of information. There is the nav edges. These are the borders of your nav data. The distance between the nav edge and the object is what you define with the nav agent radius. Nav edges are defined by the start and end point. So this gives you a direction. That's good, because if you do a cross product with the app vector of the world, you get the nav edge normal. If you are on a nav edge and you follow this direction, you get to the one in front of it. So now you have a way to measure corridors, because a corridor, a narrow space, is always defined by two nav edges. So what we did is the following. We created sizes to categorize our AIs. This is like your cloud size, your t-shirt size. Every enemy will fit in one of these. We have very small, small, medium, big, and very big. Very small is what we use for our nav agent radius. This guarantees that our smallest enemy will be able to move anywhere in the world, and it will not get stuck against the objects. And the issues with the very big one. If a very big enemy fits in the nav data, it means any other enemy can pass. So let's figure out which places are not big enough for the very big enemy. So what we do is this. We grab the very big enemy radius, we'll multiply by 2, so we get the entire capsule. And then we know that on each side of a narrow space, we will get the nav agent radius margin. So we don't need to account for that. We can subtract it. And what you have left is the distance you will need to have in between two nav edges to fit the biggest enemy. So with this distance, during the cooking process, we do nav traces every 25 centimeters for every nav edge in a tile. And if there are no hits, it means the biggest enemy fits. We don't need to do anything. Any enemy will pass through without problems. But other nav traces will have hits, like in this case. And we know the very small enemy fits. We know the very big enemy cannot. Let's figure out which ones can fit in between. What we do is we get the hit trace distance, and we match it to one of the sizes, in this case, the small size. This is an ideal scenario. There is two nav edges, and they are parallel, and there is only one nav polygon in between. But in real scenarios, you will get something more like this. Sometimes you get like a funnel with a wider entrance and a narrower exit, and various polygons, and each nav trace each polygon will be hit by several nav traces. So it's important you get the shortest distance hit by a polygon. In this case, the yellow squares indicate that. Otherwise, you will mislabel the polygon, and your AIs will get stuck. So once you get this, you need to put this information in the nav data. And the way Unreal has to do this is by the polygon nav flags. Unreal only uses two values, 0 if there is no nav data, so you will see a hole in your nav mesh, or 1 if there is nav data. And that's cool, because if your nav flag is 1 or bigger, it means there is nav data, and it's up to you what that number means. So we created nav flags for each size. What we do is we match the size of the corridor with the flag, and we know we can use this flag, the small capsule flag. Now we need to figure out which nav polygon to flag. And what we do is, once we know the nav trace that has the shortest hit distance, we grab the polygon closest to the nav trace start. And since you're going to trace from both sides of the corridor, you will cover all the polygons in a corridor. Once you get that, you can grab the nav node polyref. This is a unique identifier for your nav polygon. If you use this against your nav data, you will get the polygons with the vertices and all that. OK, we have everything. We have the flag and the polygon. We have a special object to grab this information, and we put that inside. The way the system works is that when we generate nav during the cooking process, then we start analyzing its tile in parallel. We do this multi-thread with an asynchronous task running in the background thread. When a tile finishes analyzing, it will return a collection of polygons and flags to use in all the narrow spaces inside. What we do is, when all the tiles finish, we merge that information in one collection, and we loop that. Then, using the nav node polyref, we can find the polygon in the nav data and replace the flag with what we just found. When the process finishes and the nav generation finishes, this is what we get. We get all our narrow spaces labeled in the nav data, and now we can read that information. So how do we read that? It's very simple. There is something called navigation filters in Unreal. This is a piece of logic that will run during your path calculation. And you can manipulate the path, saying, hey, favor these polygons, these flags, or exclude these other flags. So what we do is we graph the capsule size of the capsule radius of the query, or the enemy calculating the path. And we tell it, hey, let's find the flag that will match your size. Let's say we have a big enemy, so the big flag. And let's exclude anything smaller than that, because you will not fit. So we exclude for the big enemy, medium, small, and very small are excluded. Then we make sure we pass this navigation filter to our movement request. For us, this is the default filter we use for all our enemies. but we have other filters custom made that inherit from this one. I will give an example of this later. So you pass the filter to your move request, and this is what you get. When you path from the small enemy, it will automatically know, okay, yeah, I can use the small corridors. I'm a small enemy, all good. But the bigger enemy is actually a medium enemy, and it will exclude its path calculation will exclude all the smallest sizes. I will only pass through the medium capsule. So now we have data, we have a way to read it, and we have paths going through places that will work. But we still have another problem. The capsule agent radius, because as I mentioned, the agent radius guarantees that an enemy with the same capsule radius will not get stuck against the environment. But we are using enemies much bigger than our agent radius. We're using the very small size for the agent radius, and we're going to use very big enemies. And we need to figure how to fix that. When you calculate the path, this happens in Unreal. You get the path, and there is a piece of logic called stream pooling that will guarantee your path is the shortest possible. To do that, Unreal runs the simple stop-it funnel algorithm, which what it does is adjust the path to the corners and removes any extra points. And this works very well if your nav agent radius matches your AI, but it doesn't for us. Unreal offers a way to move the path away from corners. It's called offset from corners. This is a function you call on your path. You pass a distance, and then the path will be displaced. It will be offset from the corners, but this causes issues. You canceling this corner, suddenly the corner has 2 angles instead of 1 because it's splitting the point. Other cases like this one has a weird zigzag, and your AI is going to look weird while working there. And in worst cases, your path is out of the nav because this is displacing the start and end points of a path segment, and it doesn't take into consideration what happens in between. We created a different way to do this. I present you the good enough path offset. Good because it moves the corners away, no more corner hugging. Good because corners make sense, it's only 1 angle as you expect. Good because our path is within nav data, and enough because it's the most expensive algorithm of the 3 to run. But we have fixes for that. Let's see how it works. When you calculate a path, you don't only get the path, you can also get the nav corridor. This is a compilation of nav polygons your path is going to cross. Within the nav corridor, you get the nav portal edges. These are lines that connect one polygon to the next one. These are the lines the nav offset algorithm from the Unreal uses to displace the path. And that's why you see split points, because sometimes you get 2 nav edges per point. Nav edges are defined by the right and left point. And in every path, when you calculate a path, with the exception of the start and the end of points, every other point is going to be in one of these points, right or left. This looks like mirror, like right and left are mirror, but this is actually right, because what happens is the nav corridor is calculated from the end of the path to the start. So if you go from end to start, left and right makes sense, but that's not important, really. The algorithm starts with the most expensive part. We do a nav trace from the very beginning of the path to the next point. If there is no hit, that's good. We can see the point, nothing to do. We do then a nav trace to the next point, and there will be a hit because the trace is going out of nav. And that means there is a corner or an angle you need to offset. We are done with the expensive part now. So what we do is we graph the nav path segments that conform that corner, and we trace equidistant parallel lines, perpendicular lines to it. This is what I mean. There are 2 perpendicular lines that are at the same distance from the point you want to offset. A perpendicular is very cheap operation. You negate the y, you flip x and y, and there goes your perpendicular. Then you connect the endpoints of these perpendicular lines, and you form a triangle. This is a triangle base. Your offset direction candidate will be the line that connects the center of the triangle base to the point you want to move, something like this. There is an exception for this. You may get an equilateral triangle where all the sides are the same size. And when that happens, the center of the base will be the exact same location as the point you want to move. So there will be no line connecting. You need to calculate, in those cases, the triangle height, and that direction will be the same one as the blue one. And you can see the blue one is pointing outside the nav. If we move the point that way, it's going to break everything. So there is an extra step to make sure that points the right way. You grab the nav portal edge at that point, and if you're on the right side, you get the direction right to left. If you're on the left, you get the other one. You do a dot product against this line between your offset candidate and the line, and if the dot product is smaller than 0, you're pointing the wrong way. You need to flip that direction. The purple direction is our perfect candidate to displace the point. Now all we need to do is scale it to fit the capsule. You take into consideration the agent radius, the margin to the object, and the capsule radius, and you get your new point in your path. What you just saw is the first point in this example, the first corner. You can see this can get expensive if you have very long paths because you are doing up to 2 nav traces per point. But let's see how we handle performance in your game. First of all, this is multi-thread. Unreal supports navigation operations in multi-thread. So what we do is we calculate the path, and then we send all the information to a separate thread in an asynchronous task that runs in a background job, and then we wait for the result to come back. This usually takes between 0.2 and 0.5 seconds. We are fine waiting that time. We don't need immediate movement, usually in our game. We also control, we have a frame budget. Even though we are not in the game thread, we want to control how many frames it's taking. And we log when it's taking too long, because thanks to that, we discovered that we had issues. We had bugs with nav generation where the nav was too complicated and the path were doing weird stuff. And we had bugs with gameplay where sometimes calculations will fail and some AIs will try to go to the world origin, to the 000 location, calculating an enormously long path. So we fixed those bugs thanks to logging these cases. We skip paths that are just straight lines, and lucky for us, those are most of our paths, because when an enemy is in combat with the player and it calculates a path to approach the player or move away or move to a side, it's just a straight line. And you don't need to displace anything in those cases. Those are gonna work. So we skip all those, and we're skipping a good chunk of the path calculations in the game. And then on top of that, we use the significance manager to limit how many active enemies we have in the game. We allow up to 20 enemies. Within that, we have level of detail and tick aggregation to enable and disable things. And it's very rare, out of the 20 enemies, all of them are calculating paths. And even if they do that, it's multi-thread. And most of them are going to be combat paths that are very simple, that don't need to be offset. So we keep at bay performance, and we rarely see it in insights. And when we do, it's usually because bugs. Okay, when you have the information in the nav data, when you can read it and you calculate paths, this happens. There is a big enemy, the medium enemy, that is going to chase the player through the only corridor it can use. And the small enemy is going to use whatever is closest, because he can use whatever he wants to do. And this works very well. From this moment on, we don't care what the designers or artists do. They can just do any size enemy that fits in all sizes, drop it on any level, change levels. We don't have to revisit parts of the wall. We don't have to change nav volumes. We don't have to worry about anything. This just works. So it's scalable to not only this game, but other games or other demos we might want to do. Okay, we move. Let's see how we decide when to move. Decision making. We use the gameplay ability system for absolutely everything in our game, and that includes AI too. When the behavior tree runs and chooses to run a behavior tree task, the actual action of the task happens in a gameplay ability. Let's use an example. We have the approach target at behavior tree task. This is the task the enemies on the video were using to approach the player. Designers can set different data in all these tasks. For example, whether the AI should walk or run. The small was walking, the bigger one was running. Whether we allow enemies to walk off ledges, because through movement, sometimes we allow enemies to drop from platforms, not using an uplink, but by natural movement. Or which animation you should play, which is defined by animation gameplay tag. I will explain how this works later. All this data is packed in a payload that is passed to the gameplay ability, and the gameplay ability will use this data to run the actual action. Two things can happen from this moment. Either the behavior tree task finishes, and it will end the gameplay ability, or the gameplay ability ends, and it will signal the behavior tree task to continue the execution of the behavior tree. Let's see an example. Here we have 3 tasks. One that plays a combo animation, one that moves the enemy away from the player, and one that plays the idle animation. The first 2 are ruled by the gameplay ability. The gameplay ability plays the animation when it's done, signals the behavior tree task to continue. The second gameplay ability will do a movement request, and when the distance is far enough, it will just finish. And the third one is the gameplay ability is playing a loop of the idle animation that will play forever. So in this case, we use what we call the task timeout. Every task we use in Lords of the Fallen has the ability for the designer to set a time for how long it should run. So in this case, the designer says, hey, you run for 2 seconds. And when the task detects it's been running for 2 seconds, it will stop the gameplay ability, which will stop the idle animation, and the behavior tree will reevaluate or whatever it needs to do. this is super useful for us because now we can control combat in two different ways. We are heavily driven by animations. So sometimes we want the animation to decide the rhythm of the combat, and sometimes we want designers to orchestrate that. Like, I know you move 2 seconds to the left and then 3 seconds backwards, and then you play this animation. So you have full control in a very flexible way. Everything we do is data-driven, whether it's possible. For AIs, we have something that is called the character data asset. This is a data asset that compiles other data assets, data tables, and other values you can set directly there. There is a lot of information here. We can set the equipment, which armor, weapons, and other stuff the AI can wear. Stats, we have up to 145 values per enemy designers can tweak. Loot, what kind of loot, the quality, and the probability of it. Gameplay data, this is the gameplay abilities that will be granted to the enemy, but also things like how the camera should behave when the player locks on an enemy, because depending on the size and the velocity, the camera will behave a different way. And then we have animations and AI. Let's dive into these two because they're important for the talk. In animations, we set data like blending times and other stuff we need for the animation blueprint and other logic we have. Among the data we set, we create a map. The map where the key is a gameplay tag and the value is the animation asset. These are the gameplay tags designers are going to use in the behavior tree tasks when they want to use a specific animation. We have two types of maps. One is for montages. These are your one-time animations, things that have root motion, like the death animation, take one step to the left, or parry an attack. And then we have sequences, which are more your loop cycles or things you need to blend with other animations, like your walking cycle or your idling cycle. I mentioned we are heavily driven by animation, and this is a good example. I have to tailor this image for the talk, because in reality, there are 54 montages and 17 sequences. And that's for a simple enemy. If you look in a boss, it's going to be way longer, because there are more attacks and things they can do. So it's very important for us we have a good organization of all the data, so designers don't go crazy when looking for what they can do. Then we have the AI data asset. This is where we set things for perception, how far you can see or hear. Navigation data, for example, we allow some enemies to go through fire, but others need to go around. And that's where we use the custom navigation filters, because if we set here navigation data, hey, you cannot go through fire, a filter will use the fire flag to exclude from the path calculation, and the path will go around the fire. And then we also define the most important thing, which is the behavior trees to run. We have what is called the master enemy behavior tree in Lords of the Fallen, which is the behavior tree any enemy will run. And then to that, we inject all these dynamic behaviors, which are the specific things of the AI, like how do you behave in idle, in combat, or patrolling. Every enemy will behave in a different way. Every enemy will have different behavior trees. We use all this data in what we call the combine approach. When the AI possesses the character, we run the master enemy tree, and then we get all those behavior trees from the data asset. But we also run a state tree. That's the combined part, behavior trees and state trees. We have what we call the combat state tree. This is a high-level tree that reads perception data and defines which core state the AI should be. Idle, nothing happens. Caution, you heard something, go to investigate. You found what you were looking for, prepare for something else, and combat is to engage into the fight. This information is passed to the master enemy tree, and then the tree will decide which branch to run. Simple concept, easy to understand, easy to debug, but reality is a bit different, and you end up with something like this. By the end of the project, we have a massive master enemy tree. I have to collapse it so I could actually zoom out enough to show it. Many things happening here. Idle is 10 different things, because among other stuff, patrol is a form of idle for Lords of the Fallen. Found and causing states can run up to 5 different behavior trees depending on the enemy configuration. Combat is not only fight, is how do I fight when there are other people targeting the same player, and how do you react to the combat situations? How do you react to parry, to block, to dodge? And then there are other stuff that will happen no matter which other state you are. Those things you need to react to. I will explain more on that. This was an issue because towards Lords of the Fallen 2, we wanted to do deeper behaviors. We wanted to do more complicated stuff, and that implied to plug in more stuff here. And it was very easy to break things. It became a priority juggling game where what goes to the left of what, to what's higher priority. And people didn't really like to debug these things. So we needed a better approach for Lords of the Fallen 2. And we came up with the reaction system. The core idea here is we want to reuse everything we did for Lords of the Fallen. We have 100 behavior trees in Lords of the Fallen. With no way we are remaking them. And we want to use them as a base to Lords of the Fallen 2 to construct better and iterate over that. And we want to be more data-driven where possible. So we don't have to go to this massive asset to plug in things. A reaction is something that is not a core state. It's not idle, caution, found, or combat, but can happen in any of them. For example, during combat, whether you parry, block, or dodge, soulfly, special ability of the player, melee attacks, can you parry them? Magic and projectiles, can you block or dodge? And then if the player has a special ability and staggers the enemy needs to react to that. It needs to be a stagger. We have the other situations. What happens if your target goes out of reach? What happens if the player goes to a place you cannot reach or goes out of nav? You need to deal with that. We allow RS to destroy the environment. If the player, while in combat, hides behind a crate, the enemy will reach the crate, break it, and continue. And this is the player will not notice there's been this swap in the behavior. Rubber banding, we don't allow enemies to be lured very far away from their designated areas where they originally spawn. So if they detect they are too far, they're going to try to trigger a behavior to come back slowly to tell the player, yeah, I'm not going that far, you come to me. And then we have what we call wait first encounter. These are tailored situations for the gameplay experience of the player. So for example, let's say the player gets into a castle, and we want every time for the player to see these two soldiers patrolling down some stairs. What we do is we tell the AI, hey, you have a patrol, and you will go downstairs, but you don't start patrolling until the player is at this exact location looking this way. And for Lords of the Fallen 2, we are adding way more reactions for combat. We are adding more complicated with first encounter situations and other stuff. So we need a better way to organize all this. This article came through our desk, reactive behavior trees, a way to deal with these situations. I will link it at the end of the talk. I recommend you read it. We iterate on this. We have a different approach. So what we do now is the AI controller processes the enemy, and we run a custom state tree component. We double down on state trees, because by the time we started Lords of the Fallen 2, they evolve and they are much better now. We can do much better stuff, more complicated things. And this custom state tree runs two types of state trees. It runs the perception state tree and the reaction trees. Let's see what's what. The perception state tree is what we have before named combat state tree. This is a state tree that reads perception data and decides on a core state, idle, found, caution, etc. The difference now is that this state tree will actually run the behavior tree. We don't have the master enemy tree anymore. We dismantle it into pieces, and we are relocating things here or there. So what happens is when you get into combat, we run the behavior tree combat. We don't pass this information to some other asset. In parallel, we are evaluating different reaction trees. These are simple state trees designers will create, where they check conditions in the world and in combat and context, gameplay context, to decide whether the AI needs to react to something. These are small blocks to construct deeper behaviors. Let's see an example. Let's say the enemy is in combat fighting the player, and while we are evaluating the reactions, we are evaluating the attack reaction, whether we can parry a melee attack. Chances are good, the enemy can, and the reaction says, hey, you can parry the following attack. So we send an event to the perception tree, and we tell it, hey, you can parry, and this is a behavior tree you will run for that parry. What the perception tree will do is it will interrupt the combat BT. It will jump to the run reaction, a new state that can only be accessed through this type of events. It will run the parry behavior tree attack, will play the parry animation, apply some stats, whatever it needs to do. And when that's done, the perception tree will reevaluate and most probably continue to combat or do whatever it needs to do. This works very well, and we did some iteration on that. First of all, we were ticking all the reactions all the time, and that didn't make any sense. Why will we check for parry attacks when the enemy is in idle? If nobody's attacking it. So we created the reaction tick conditions. These are very simple and quick to check conditions that are usually either some gameplay tags are present in the character, or there is a gameplay event we send to provoke a reaction through the gameplay. So we check these tick conditions first, and if they don't pass, we don't even tick the tree. We ignore it like the reaction doesn't exist. So quite flexible, but there is more to it. This is how the perception tree looks like. This is the merge between the core functionality of the master enemy tree and what we have before. We have lots of conditions that are the white text. We converted some decorators into state tree conditions. That's very easy to do. They follow the same logic. And we have the old states, right? Combat, found, Gaussian, idle. But also we have new states. We have debug to force behaviors and to test things. We have patrol is its own new state because it's more complicated than Lords of the Fallen 2, so it needs to be its own state. And then at the bottom, we have the run reaction state that will be only accessed through that event. We want more data-driven, so data-driven it is. We have 2 arrays for reactions. We have high priority and low priority. We only need 2 levels of complexity because either a reaction is something that needs to happen right now and cannot be interrupted, or the reaction is something not so important that can be interrupted. To give you an example, let's say the enemy is rubber banding and it detects it's too far from its spawning area and is coming back. And then the player attacks the AI and the AI needs to parry. Parry is more important than coming back. So we will interrupt the rubber banding reaction because it's a low priority, and the high priority parry will play the parry. Things will reevaluate, and chances are the enemy is still too far, and it will rerun the rubber banding reaction and come back. Each of these definitions look like this. This is the attack reaction. We have a gameplay tag to define it and find it in debug. We have the state tree the designer will create to run the conditions, the priority, whether the reaction is enabled or not. We can enable and disable reactions when we want. This is very useful for debug and isolating issues. Queue. Sometimes, no matter what your priority is, we don't want to interrupt things right away. For example, let's say the AI is playing a very long combo, 10 seconds combo that is pushing the enemy forward, attacking the player. And while that happens, the rubber banding triggers and says, well, you're going too far. We don't interrupt the combo behavior tree because for Souls-like games, it's very important to keep consistency in combat. That's how the player learns the combos and how to defeat enemies. So what we do is we queue the reaction and we wait for the combo to finish. And when the combo is finishes, if the queue is still there, then we run the reaction. We call it queue, but it's only one slot. So if another queue reaction happens, we replace it. If another immediate reaction that it needs to not be queued, but to run right away happens, we remove the queue. It's only one at its time. We don't stack them because that doesn't make sense. You will get that with situations where you play the rubber banding, and when it's finished, it will parry no one because it was on the stack. So no stacking for us. Cooldown for the reaction, so it doesn't run too often. It's gameplay ability system style, attack and a time. Some tags we can add to the character while the reaction runs, and they will be removed when the reaction finishes. And the tick conditions, which in this case, the gameplay tag event attack incoming needs to be present for you to consider to evaluate that state tree. And we have one last issue with this. I mentioned that we don't have the master enemy tree, so we are running behavior trees as single instances, single pieces we run here and there whenever we want to. And that's an issue, and that's because how Unreal handles memory. Usually you have a master enemy tree with subtrees. When you run a behavior tree, you get an entry in the known instances. This is the long-term memory, the persistent memory of your behavior tree component. Every new behavior tree run will get an entry with a pointer to the asset, a copy of the behavior tree memory, and the instance data. This is data like who's your root node, or what's the execution path needs to follow to get to this behavior tree. When you run a subtree like the idle, you get an instance tag to it, and you get each entry. This is your temporal memory of your behavior tree component, and you get an index to the known instance, a copy of the memory of the tree, and execution data with like which nodes are active in your current behavior tree execution. When you run a different subtree, you get a different stack. The stack renews. And the way Unreal works is that if you run the combat, and then you run idle, and you get back to combat, memory stays because the memory is copied back and forth. And we have an issue with this because we use utility in our combat. So when we pick up a combat behavior tree subtree, we record it in the behavior tree memory just to avoid repetition the next time we run combat. When you do this, you are writing to the instance tag to your temporal memory. And when the instance tag is cleared out, every entity that is removed from the instance tag is copied back to the long-term memory. So you copy back to the long-term memory, and once you run the behavior tree again, you get that copy back to your instance tag, and there is this back and forth of restoring memory. This didn't work for us, and for a reason, because when you stop a tree, you clear out all the memory, you lose it. And we were running trees and then stop it and run another tree, so we ran combat, and then we run a behavior tree reaction, and then we get back to combat, but they are single runs, and our memory is not there, and the utility was picking the same options again and again. So we had to fix that. What we did is in the stop function, we do a backup. We use the same variable the known instance is used. We just have it somewhere else. So we have the instance, the short-term memory, known instance, long-term memory, and our memory, which is real long-term memory. So we make a copy of the instance there. And then in the function push instance, we restore it. When the behavior tree runs again and is put back into the instance data, we then do the copy back from our long-term memory. The reason we do it in this function is because this is the function that calls every time you run a tree. Whether it's because you call a start tree on your core tree, on your master tree, or because you run a subtree through the run BT or run dynamic behavior tree task. So we now have a way to back up and restore the memory the same way Unreal does. And we have an exception to this. We only back up nodes we care about. We don't care about nodes provided by the engine, because we don't want to worry about Unreal changing how it handles memory for its own custom nodes and breaking things. And we only care about our utility, couple custom cooldowns, and some other things. So when we restore the memory, we check the nodes in the tree that is about to run, and we just select the memory we want to restore. With this system, it works very well, because now designers don't need to worry about how the massive master enemy tree grows exponentially. They can just create single state trees, put them there in the data asset, and everything's data asset driven. So very flexible, much easier to handle, and it can scale. You can do whatever complicated behavior, and you will have just a growing data asset, and that's about it. Okay, we move, we decide, and the whole point is to go into combat. And there are two situations in combat we need to handle. One is, what happens when your enemy needs to pick between two targets? Because we have co-op, online co-op. You can play with your friends. So what we do is we apply a score to each target. This is the aggro score. The aggro score is a calculation out to 4 points. Whether the closer to the target, the better. What's the damage that the player is inflicting on me? It's not only how high the damage is, but how long you sustain it. Aggro damage is an artificial score we can add whenever we want to create the sensation of aggressiveness. If we want an enemy to keep targeting the same player and no matter what, don't get distracted. And then the swap target score is like a cooldown to avoid ping-pong in between targets. There is also the decay rate. Some scores will be diminishing to 0 frame by frame, and that's driven by curves designers can calculate. So this is how it looks in reality. The enemy is picking the player in the background. Green line means the distance is close, and the blue one is the swap score. The other player attacks the enemy, but it's only attacking rarely, so it's not sustained attack. But if we sustain the attack, we will become a higher danger to the enemy, and the enemy will pick us as a target. So there it goes, and reaction, it dodges it, and then it picks the player. We get the swap score. The damage disappears because it's decaying, and as closer it gets, the green line goes higher because the distance is shorter, higher score. And the situation repeats again. If the other player wants to distract this enemy, we'll need to attack consistently to get distracted. With this same concept, we handle the other situation. What happens when many enemies attack one player? You cannot allow that. You need to balance the combat, otherwise it will be very unfair. So what we do is, using the aggro concept, but also the danger concept, is how dangerous an enemy will be against the player. And this is a formula that calculates the damage an enemy can do on the player, the attack power, and we consider how dangerous it is. So we have 3 roles. The first role is attacker. Attacker is, I'm gonna be super aggressive. I'm gonna beat the player until it dies. And if the dangerous is high, we will allow 1 enemy. If it's low, more enemies, up to 3. So we can have 3 simple enemies, or 1 boss and 1 simple enemy. We play with that. When the attacker roles are filled, we move to the cover. Cover will be around the combat. They will be trying to get to a position where they can become attackers, and they will attack rarely if they can. And when the cover roles are filled up, then everyone else is going to be a spectator. They're going to be in the back of the combat, moving around, attack very rarely, but still attacking. Nobody's idle in our game. And they will move in and out, try to become the other roles using that aggro score and that dangerous score. And this is how it looks like. If you pay attention, every enemy is going to join the combat. Every enemy will become an attacker. Each role has its own behavior tree that can be defined in the data asset by the designers. So the guys with the stick, when they are cover or spectator, they use range attacks. When they become attackers, they will try to staff the player. And this creates a nice dance. The combat is alive and things work pretty well. And you just see the three systems we have that we can use in other games, because this will work with a shooter. Your cover is behind cover, and your spectator might be doing grunts like he's reloading and stuff like that. And we're extending this for Lords of the Fallen 2. We are doing more complicated roles, and so far so good. So this is the end of the talk. I want to thank you, everybody, for being here, listening to me. I want to thank Epic for giving me the opportunity to be here, and from the bottom of my heart, to the people that started Lords of the Fallen and continue the development, because without them, I will be a pretty face behind a screen instead of a pretty face in front of one. So thanks a lot to you all. Thank you.